tell us these are obvious things and we don't need to know. Obviously, Internet of Things is connecting everything at any time. We have had it for a while. Let me see. I'd set my pen as well. Yeah. Connectivity of things, connectivity anywhere in any location has been around for at least for past 2 decades. One thing has been added recently, when I say recently, probably it's around the past 10, 15 years, is being able to connect physical objects. Not necessarily the objects themselves, putting sensors in environment in somewhere which we can collect physical data from physical environment and communicate that to backend servers. Most of the time we are interested in communicating that to internet backbone, but not necessarily internet. Sometimes could be an intranet machine-to-machine communications. And that is an umbrella term, we use an umbrella term for that, which is called Internet of Things. But generally it's just connecting sensors and actuators which can make change in the environment and making their data and functionality available. Probably for the first time in human history, we are able to connect more or less near real-time data from our surrounding environment. You can put more or less sensors everywhere. In Paulo's examples, he showed sensors everywhere in the city, in the industry, everywhere, and we can collect this information and communicate them in real time. We more or less have our planet in our hand if we collect all this information, and we can follow what's happening, follow the data, and analyze that. But practically, that's the picture you get, because most of the sensors will send the data in different formats, in different quality. Even you're collecting, let's say, temperature data from around the city. If you have multiple providers or multiple sensors, the quality of sensors could vary because of the changes in the environment, or different manufacturers might produce similar sensors with different accuracy, with different formats they send. Then the big challenge is we are collecting lots of data, but making sense of that data, especially for machines, is a big challenging task. IoT data has a few specific characteristics which probably makes it a little different from our traditional web data or textual data. One is the multimodality. The data could be like image data, numerical data, could be text data. Someone can tweet and say there is an accident in a part of the road. That still can be a real-world data, and if we can use that data, combine it with other information we have, it make it more interesting. Because the platforms and most of this infrastructure we use in IoT are in the wild, are not in a controlled environment, the data can be noisy. And that noise is a big issue often in IoT applications. For example, we use IoT devices in monitoring people's health and well-being, which I talked about it on Friday. And when you're monitoring people and monitoring their health or body vital signals, the accuracy of your data, it becomes a really important aspect of your design, and the noisy data often can basically hinder designing more reliable systems. Most of the data is time and location dependent, because when you say temperature is 35, well, today it probably is around 25, 27 degrees Celsius here. When you say 27 degrees Celsius, if you don't associate time and location, that data is not very meaningful. Maybe 5 hours ago, this room's temperature was something different. Once you add time and location, then you add context to your data, and that data becomes meaningful. And telling machines the data, or giving them the data, you need to give them the context, you need to give them the spatial and temporal information to allow machines to be able to make sense of that data. Often the data is also the environments we operate are dynamic. When we say dynamic, means when you're collecting data, depending on the changes in the environment, the quality, accuracy, distribution of that data might change. If you're collecting data from this room, depending if there is a lecture, there is a departmental meeting, there is, I don't know, nobody's here, or there is windows are open, or there is a fire, the type of data you get, it continuously could change. And the more your system is in the wild, or more you have elements of change in your system, this dynamicity becomes bigger and bigger challenge, especially for analyzing data. Lots of IoT systems will rely on crowdsourced information, not like you hear a lot like this project which people deploy sensors, they collect information. Often these applications are very, very interesting, But when you're collecting crowdsourced information, the reliability of that data and a trust element in that data becomes important. One of the examples, if you remember during the Fukushima Fukushima nuclear disaster, a group at, I think it was MIT, they published a blueprint telling people in Japan how they can use their mobile phones, connect a radioactive activity monitoring sensor and put it outside the outdoor and monitor the radiation level. And there was a platform which people could actually go and program their devices, put the sensors outside, and start reporting the radioactivity levels from the environment. Brilliant application, because before big organizations, big groups actually could move in and deploy sensors, give information, citizens could share the information from the environment and help each other. But around that time, if you looked at that platform, we could see significantly different readings from the same location. The reason was some of this data, some of these devices were not calibrated correctly. Some of them were not programmed correctly, or unit of measurement wasn't correct. Then you were getting lots of data, but often, in some cases, making sense of that data was a challenging task, which is correct, which one is not. At the same time, you can think of these systems can be easily basically biased if people start adding fake data to your system. Then once we are putting our infrastructure in the wild, this crowdsourced information, reliability and trust becomes a key issue. And often the processing requirements are near real time. As often when we process, let's say, web data, textual data, or look at like how, let's say, most of the early generations of web-based systems that work, they usually rely on batch analysis of the data. Here we have the data emerging almost online and near real time, and the processing should also follow that. If you're managing traffic, if you're providing alerts, if you're monitoring someone's health, that the notion of being near real time and in your analytics also becomes an integral part of your system. And obviously, security, privacy are always an integral element of it, because most of the IoT data will be somehow related to people, would be personal data. Even sometimes you think that data is not personal, but associating that data to something else, you can actually start inferring information related to an individual. An example of that, in my previous office, we used to have sensors around the office which monitor temperature, noise, some environmental elements. And we were involved in a European project called City Pulse, and my colleagues wanted to have some test data. I think there was a group in Germany, and they wanted to have some test data to basically use some IoT data for a prototyping before we actually rolled our main application. They wrote to me and asked if they can use the data from my office. So yeah, who cares? Temperature, light, noise data from my office. Yes, of course. And I talked to our IT department and we opened the data and they started using it just for simple prototyping. One day I turned up, I used to coordinate that project. One day I turned up in a meeting and I hadn't done my homework. I hadn't prepared my report, whatever I needed to do. And, well, I'm recording. I said a little lie, and I said, oh, I've been very busy, I've been working for the past 2 weeks, and I didn't have time to work on this report. In 5 minutes, my colleagues put the noise data and the light data from my office and was flat. I was on holiday. And that's simply as a notion, when you collect data, often you think this data is not personalized. You collect temperature data, noise data from this room, and you say, well, the security is not important, privacy is not important. Well, you might never thought of actually, if that data gets linked to something else, how it can be used. Understanding the data, the context of data also is very important. If you are say, analyzing data from a wide deployment in a wide range deployment in, let's say, in a farm, the density of that deployment is also will have something to say about your data. For example, if you have too many sensors in closed locations, obviously your granularity is better and you have better information. If the sensors are far enough, then the accuracy of the information you're collecting, you have to be aware of that. If you collect the data without understanding, without having information or giving the machines or algorithms that analyze that data, without giving them the contextual information, maybe our analysis also can be easily biased. And that's something when you analyze and design analytical algorithms for IoT, you have to be aware of it. For the next 2 days, I'll try to give some examples and show some practical examples of actually how this could happen and some of the solutions which you can apply to resolve these issues. But if you look at the IoT itself, it started maybe in late 90s, early 2000, with people working RFIDs and tagging and tracking the basically objects, physical objects. The second wave of IoT work or IoT research started with wireless sensors and actuator networks. And if you go and look at most of the publications in IoT domain, in early 2000, most of the people worked on wireless sensor networks, routing algorithms, energy efficiency. This work still carries on. But over the years, we have built more reliable hardware, better infrastructures, and we see more and more commercial solutions. Like companies have now adapted. Paolo showed some examples from like big companies providing IoT platforms. What is happening probably is we are collecting now more and more data, and the future of IoT applications more or less relies on how effective we can use this information and how we can transform this data to some intelligence, to some insights, which we can feed it back to system or use it for controlling or intelligent decision support systems or intelligent decision making systems. Over the, at least, I've been working in this area for the past 10 years. I've seen lots of large deployments, lots of changes in the sensor technologies, in the communication technologies, protocols. But still, we don't have really integrated, say, IoT solutions. Like internet is more or less, more or less is a standard. Like I flew into this today here. I switched on my computer. I get connected to the Wi-Fi here. That's a perfect example of it's a perfect example of a good interoperable system in terms of hardware, software, everything. I'm connected, and at application level also I'm connected because all the universities in Europe, they have agreed on a Wi-Fi system, and all they share that you can authenticate wherever you are and you get connected. That's a perfect example of you have connectivity from the physical layer to talk to the application layer. No matter where you are, where you connect, still you have the same service. But in IoT, Paolo showed many examples of that. You have lots of diversity, lots of systems which they work in their own merit, their own environment, and interoperability is a big issue. We are not the first people encountered a similar problem. In early 2000, Tim Berners-Lee, who invented the web, himself, he and his colleagues, they published an article and suggested this idea of semantic web. And the idea was, the notion is, when you browse the web pages, when you look at the web pages, most of the processing is done by the human cognition, human brain. The browsers, they open the page for you, but you read the page, you interpret the page. If you open my university homepage, you decide where's my email address, where's my phone numbers. And if you look at the HTML code, if you're familiar with the HTML codes are just a series of tags and messy text, which are not easy for machines to read it. I don't know if you have tried to write programs to basically read and separate different tags from the HTML pages. As soon as your website provider changes their template, your program doesn't work anymore. I've done it a few times, and because the pages are designed for the view of them. Like HTML is very effective in telling how the page should look like, what color it should be, how the table should look like, but they're not designed for the machines to be able to read and understand that data. In early 2000, lots of researchers in the semantic web domain, they started looking at solutions which they can add more structured information to the web to make the web data more accessible to machines. Then machines can do better search, find better information, and access the content of the pages better. And that domain is called semantic web. And the idea was to allow the humans and machines to work in collaboration and cooperation. If you want to apply the same philosophy and the same concept in IoT, we are interested in creating data structures which machines can easily read and understand and integrate it into the existing systems. Then if I have a temperature sensor, ideally that temperature sensor should send its information using a common language, which doesn't matter what platform you're connecting it, which system you're connecting it, you just program your sensor, you send information, and any existing platform should be able to take that information. That's more or less the idea of creating an ideal system, which you can get data from different sources, from different environments, and they can be integrated. And most of the research in applying semantic technologies to IoT is focused on this very basic problem. If, like, all the people working in this area, all the providers could just sit and agree in a week, in 10 days, and agree on a common language, I don't think we need any research in this area. But that never happens. Different companies were different research groups, different people based on different focus, different interests they have. Always they publish their data in different formats. And that's why we need to do some, let's say, information engineering, knowledge, data engineering to make that data effectively be able to interoperate between different platforms and different systems. There are several work in this area. I'll provide some examples of that, but most of them will rely on notions like this. You want to start with modeling your system, modeling your concepts, and you say what concepts you have in the system and how different concepts are related to each other in that system. And then you start representing it in formats which are more machine readables. I'll explain the structure, and with the next 2 hours, you should be able to get a good insight into actually what that data format is and how they are designed and why we are designing it. And if you look at most of the activities on the web side of it, on the semantic web itself, semantic web also has moved from just representing data and structuring data to creating more linked data, creating inference models, and looking at the vocabularies, and also creating models which you can query that information, because collecting and structuring data is one thing, making that data available is another challenge. That was like a 5 minutes, 10 minutes quick background to the semantic web, but most of my slides today will focus on applying semantic web technologies to Internet of Things, and I try to provide some background about those data formats, modeling aspect of it, and some of the challenges you face when you start applying some of the semantic models to the IoT. One of the key notions about IoT is obviously you have different nodes, and these nodes can be either off-the-shelf devices, can be programmable or could be off-the-shelf devices. You need communication protocols to allow your data to be communicated. It's a wired communication. In most of the cases, you have wireless over-the-air communications. Sometimes these devices, they send their data directly to internet, to the web, or sometimes they use multi-hop communications. Means the device sends its data to another device and they pass that data till it gets to the web. The key challenge is these devices are often resource constrained. They have often they work on battery power. They're battery powered. They have limited computational power, and they have limited communication capability. When I say limited, for example, we use some sensor nodes for part of our research. They are like this size. You can put two AA battery, and if you program it, depending on your sampling, how many times you sample and how much data you send. But if you use it like, let's say, in a normal way, the battery will last around 2 months to actually can operate. The operating system we run on that is Contiki operating system, which is around 40K. The entire operating system, probably with your program, is something around 40-45 kilobytes. Windows operating system is now around 2 gigabytes, 4 gigabytes, I don't know, something like that. You can compare your entire operating system. In terms of the processing capabilities, lots of these microprocessors becoming more and more powerful. But the more powerful they are, the more power hungry they become. And then sourcing them, putting energy resources on them, especially if you put them in an environment which you don't have powered resources, it's a big challenge. And the current design of most of these devices are, when you start sending data, especially if you're sending over radio protocols, which they are sending the data over a longer range, it's very resource hungry. They require lots of battery. That's why, for example, BLE, low energy Bluetooth, is very effective. Usually battery powered devices can operate on BLE for a long time, but BLE's range is very short. And if you're putting, let's say, designing sensors to monitor, let's say, fire in a forest, or if you're monitoring, a marine life, and your sensor is actually 10 meters down deep in the sea, going and changing the battery is not an easy task. It could be expensive, sometimes it's not impossible. And then energy efficiency becomes very, very important. Now, if you want to make the data more interoperable, more usable, I'll talk more about the techniques which you can help the networks to become more efficient. You can do data aggregation. You can create some of the analysis to it on the machine, on the nodes themselves. But generally, if you are trying to make this provide interoperability, your basic solution is to add metadata, to add some tags, some information to that data to describe it. The challenge is, as soon as you add metadata, you're increasing your overhead. If you're adding metadata and you're sending from sensors, if my sensor now is sending 2 bytes, now it needs to send 20 bytes. If you're adding that metadata on a, let's say, outside the node, you need to have a design to be able to add the metadata somewhere, which then your applications, that when they use the data, they can have access to basically the context of information, and it can extract the different attributes from your data. But in principle, what happens is you will have either programmable devices which you need to program them yourselves, or you will get some off-the-shelf devices which they usually come with an app. The big challenge is you get a new device, you have an app. You get the second device, you have another app. And the number of devices, they increase, the number of apps increase. But ideally, you want to have the data integrated to a platform. You want to use that data to be able to analyze and bring the data from different sources together. And that makes the semantic interoperability a big challenge. Then I just sum up what I've said so far. Data comes from different sensory devices. Usually it is, again, time and location dependent. And ideally, we want to integrate this heterogeneous data and to be able to use the data from different sources and combine the different measurements, the data, to be able to create some insights. And the big problem, where the problem starts, when you're adding your devices and the devices start sending data using different formats, different quality, and you need to create a format which your machines can read and understand. Giving you a practical example, when we started doing our healthcare application, we are deploying sensors in the home. And the idea is with deploying sensors, we monitor people's movements, people's day-to-day activities, and their body vital signals. And we process this information to detect infections, to detect agitation, to analyze their daily living activities and find the changes in their pattern of activities, identify social isolation, hyperactivity, or conditions like hypertension. I'll talk about this on Friday, and I'll explain what these conditions are. But when we started the project, we were working with different companies which providing devices. Let's say when we were giving blood pressure monitoring to our participants to monitor their blood pressure, the blood pressure device was coming from 3 different companies. And each device was sending the blood pressure, the same data in different formats. And every time you add a new device, a new provider, that the format changes, the quality changes, the parameters changes, and you need to accommodate all these changes, or you need to find a common way to be able to integrate that. Ideally, if you want to create a scalable system, what you need to do, you need to create a system which becomes detached. Basically, you decouple your data format, your information structure from your platform, which is going to use that information. And that's the idea behind interoperability and creating machines which can read the data and create machine-to-machine communications and machine-to-machine basically interactions once you add semantic data. Another aspect of it, once you start collecting your data, You need to think of for what purpose this data is being collected, what attributes of your data becomes important. If you're collecting for healthcare application, probably you need to know the accuracy of that data, you need to know in what frequency you have collected that data, you need to know what time it was collected, and so on. And obviously your model will be designed based on that and will provide that information as a metadata, as a semantic data to higher level applications. The second stage is, which I will talk more about this tomorrow, is analytical models which will use this data to analyze it. And once you have analyzed that data, you create some insights. For example, you monitor my information from my home, my body vital signal, and your algorithm decides probably I have a risk of having an infection. That data, again, needs to be either communicated to a clinician, or if you're sending it to another system, you need to express that data in a format which the other system can pick it up and can use it. And like my internet connection, always I don't need to program it for 20 different providers. That data should come in a format which systems can use it, pick it, and use it, and be able to reuse it in other systems. Then the data collection, in terms of modeling, first we focus on the data collection, what we're collecting, what features we collect, and the data model will focus on expressing and providing basically structure for that data. The second part will focus on analytical models, and what we extract from that analytical models needs to be represented in sort of a semantic or in vocabularies which can be used. And then that format should be in a way represented in a way which can be used and reused by other systems. Then probably for the rest of today, I will focus on those stages and explain how you can create models which can basically support each of these steps. There are also a few I just use this terminology because sometimes you hear also concept of Internet of Things, Internet of Everything, or sometimes Web of Things. Often it depends probably who funds your research. And also in some cases it's just people referring to the application. If you come across like Web of Things, the idea is the information you're collecting from the things are integrated onto the web or application level you're looking at. There are some existing already standards providing some modeling for sensory data. OGC has a set of standards which recently also they have been working with W3C to create a set of models, metadata models, and representation formats for expressing mainly spatial data, but sensory data as well. I'll try to provide some examples, and I'll show how these models are designed and for how useful they can be if you use them in Internet of Things. I took this example from a website. This shows like a temperature data, I think from somewhere in Slovenia, if I'm not mistaken. And if you look at most of the IoT data or lots of the data representations, will provide something like this. This data is easy for us. I can read the temperatures. Obviously, the degrees Celsius is what is the current temperature. You can see the historical data, and it's a bit difficult to read. These are the location information, longitude and latitude data. But if you want to give this data to a machine, a computer will find it very difficult to be able to go and separate this information. And that's what often you need. You're not giving this information to human users. You want to feed this information to a computer program. You need to feed this information to an algorithm to be able to read and analyze this data. And that's the biggest challenge. Often data is formatted for human use, and it becomes more difficult when you're taking data from different sources and you're giving it to machines to be able to read and analyze that. Probably if you look at this data, it's not very difficult to guess. That looks like a temperature data, 15, C probably stands for Celsius. Maybe you struggle a little if you haven't studied geography, which one is longitude, latitude, always mix them up. But if you know the geographical GPS coordinate systems, probably it's not that difficult to guess which one is longitude, which one is latitude. The first step for modeling it to make it easier for human users and for machines is just simply adding tags. If we add tags to this data, we have solved almost the large part of the problem. And once you add the tags, it's now finding a way to express these tags in a way which machines can read and interpret this information. And obviously, if you just rely on syntactical data, if you had changed the order, if, for example, if you received all your data in this format, you might say, well, why do I need to add tags? I always write a program, knows the first one is the value, the second one is the unit of measurement, and so on. The problem starts if you get another device and it just slightly changes the order. Now your program won't work. Or you need to make sure everyone will send it as the same format, and it often, again, becomes a challenge. And controlling that data, controlling data from different sources, especially if you work on a large scale with different systems, different providers, or if you really work on an internet scale, becomes a big challenge. Going back to our tagging, if you add just tags, just simply labels to each of this, then probably we have solved the problem. And there are very well-defined solutions to represent those tags. I'm guessing everyone is familiar with XML, right? XML has been around, and it's just this interoperable format. You just add, it's a well-defined language, you add just tags, and those tags basically provides vocabulary. There are very well-defined tools to process the XML. Each of this will represent, like, just say this is the value, a tag, and so on. There are lots of
all of them know XML.
Yeah.
We teach XML.
Brilliant. Okay. Then I can skip this very quick. Then quickly, XML is a very well-formed language. It's just represented in text. There are lots of tools to use it. And basically the structure will look like this. And then you can write lots of programs. Now it's simple. It doesn't matter what order people send information. As long as they send XML, you can write any program. It doesn't matter who programs that device. As long as you get the XML data, your system always will pick up the tags and can integrate that data no matter where that data comes from. It seems you have solved the problem. More or less it's solved, right? And also you have, if you're familiar, you can add more structure to XML. Even you can define the data types. You say this data type, I'm expecting always to see the value as decimal, or I'm expecting this to be always, I don't know, string, and so on. You can add more constraints. You can add more structure to your data. You can even check that the data is consistent, because in applications also when you get new data, you can verify, like banking systems, they verify the transactions. Here you can verify the data currently coming in the correct format. Basically it's a well-structured language. And once you've done that, you can create basically schema language. If you're familiar with the XML schema, you can create the template, you give the grammar, and you exactly define what that structure looks like. And that's more or less what we need. We needed a structure. We needed a structure in a way which machines can read and interpret it. And XML is very well-defined language, has been around for a while. We have XML databases. We can easily create these XML documents, and we can represent our IoT data in a way which we can feed it now to machines. Now, back to my example of working with different providers providing blood pressure monitoring devices, if they all send this information using this format, problem solved, right? I can write a program, always I can read, I don't know if this is if someone's, well, this can't be body temperature, but if blood was the temperature, I can always write a program, can read the temperature, can check the value, I can write rules on top of that, I can integrate it with other data, and so on. Seems the problem is more or less solved until you look at something like this. Compare this to, it's the same information, I have just changed the tags, right? And once you start changing the tags, it becomes a challenge, because then which one is correct? Which one do you say is more correct? There's no way to say which one. I mean, it's just different people might call it different. I mean, if you use tags in different languages, nobody can say if you write those tags in Italian it's wrong, or write it in French it's wrong. It's just all of the modeling aspects are correct, right? And that again brings us back to the square one. We seem to solve the problem, but as soon as we solve the problem, we created another problem, because different people will come up with the same tags with in the different vocabulary, and that becomes a problem. And that's inherently is in XML structure. First of all, XML doesn't have any ontological commitment. I'll explain what I mean by ontology. But basically, there is no commitment on hard commitments on the vocabulary. Both the XML examples I showed are correct. There's another limitation with XML is usually the data in XML is represented in a hierarchical structure. It means you have something structured like a tree structure. It's like everything is represented as parent and child. For example, it doesn't say what is the relationship between this 15 and Celsius. As human users, we know that's the value, that's the a unit of measurement. But for a machine, if it doesn't have the previous knowledge of that, it's again, you need either to hard code it into your programs, or you need to give them some knowledge for machines to understand that. And XML inherently, it just provides a hierarchical structure that doesn't say much about the relationship between different pieces of information. And that was an easy example. If you have more structure, if you have location data, if you have quality data, this becomes more and more complex. And if you have like, I don't know, data over time changes, representing this again becomes more challenge for machines. Obviously for a human user, you can always read and understand, but we are looking for models which machines can just pick up the data with less effort, or with some basic functions we have given to them, can read and understand and interpret data and can start using that data. That's ideally what we want to happen. Then summarizing, XML provides a good structure, solves our interoperability problem, but doesn't give us any modeling like commitments on the vocabulary we use. And in terms of a structure, it's a bit limited. Again, semantic web, people working on the semantic web have tried to address similar problems, and over the years they have developed some good models, structures, some representation frameworks to be able to address, to create more structured data, and to be able to represent them in a way which machines can read and understand. So let's pause it for a minute. I mean, all this, if you notice, is not really rocket science. It's just information engineering and knowledge engineering and adding metadata. However, if you look at the notion of, let's say, machine learning, over the past 3-4 decades, we have always been trying to create machines we can read, understand their data, process that data, and always we think within the next 10 years we will have machines will understand everything. And since I've been a student, always has been next 10 years. Always we think in the next 10 years. We have made tremendous progress in machine learning, analyzing text, understanding it, but still machines will sometimes struggle very with the simple basic things, which as a human we find it easy to read and understand and process it, right? The whole idea behind the semantic technologies is combining that intelligence you can program in your machines with knowledge engineering. If I can do a bit of engineering, structure my data in a better way, and then add my intelligent algorithms on top of that, then I can create machines which become much more intelligent, much more efficient in analyzing that data. Then most of the semantic modeling technologies, they focus on creating this infrastructure. Then as soon as you do that, you can write reasoning algorithms, you can write say rules on top of that data, you can query that data, you can link that data to something else, and you can start creating better insights. Back to my example of people monitoring my office, as soon as you know this is light information, temperature information, and then you have some structured data about me, and you say this data is linked to his office, and then I'm somewhere in a meeting and I say I have been working on it, you can start following these pieces of information using the semantic models and link them and start extracting insights. See, without that structure, it probably will be close to impossible for a machine to be able to track all those pieces of information and understand they are all connected to each other. And imagine if you have very, very large scale data, that because either of these become possible also, will probably require lots of resources. You need to search lots of unstructured data to be able to extract the features. As soon as you start creating structured data, suddenly you're boosting your machine's capability to be able to read and interpret that information. And semantic web technologies trying to provide that basic structure for machines. One of the key frameworks for representing this data for semantic data is Resource Description Framework, RDF. Have you come across RDF before? Okay. One of the key limitations of RDF, XML, was XML represents everything in a hierarchical structure. RDF changes that notion, and the very basic thing about RDF, information are represented in graph formats. If the data is graph, then you can create different structures and connect them to each other, different graphs. And the basic notion of that graph in RDF is something called a triple. And a triple is, let's say, is a subject, let's say is a person, for example. And let's say that person has a name, which we call it an object. This is subject, an object, let's use a different color. And something which call it a predicate, which shows the relationship. We say has name. Now, if we can represent this in a structure which use, let's say, something like an XML format or something like this, which I show in a minute an example of that, and we say a person has name, and has name means indication of that identity for that, you can write programs and say, go and find everyone's, I don't know, all the objects' name. If you say has location, then you can write a program to say, any data I get, go and find the location of that data. Means those relationships, now they have a label. And then you can write programs to go and follow those labels, follow the path to be able to extract different pieces of information from the large graphs of data you have. And that allows us to create the basic structures for creating linked data. In IoT, that can be a sensor has a value. A sensor, for example, I'll show some examples in a minute, has a unit of measurement. And then you can start saying, if you're reading the unit of measurement, go and check and find all the sensors which the unit of measurement is Fahrenheit, and then add this formula to change them to Celsius. Then if you're getting two data, temperature data, around like an environment, if one of them is sending with Celsius and one of them sends with Fahrenheit, simply a machine will get confused. But if you have structured data, you will say go and find has unit, for example, if you've agreed on that, and say if that unit, for example, the value is Fahrenheit, then always use this formula to convert them, or the other way around. Basically in RDF, everything is represented as triples, and triples are either they are an object which use a property. This is the link connected to a subject. An object, for example, is sensor 1. Oh, sorry, I should have written it the other way around. An object is room 1, and the subject, for example, is location. And you have a property we say has location. This can be geocoordinate, or it can be physical location of that room within the building. You say which floor it is and where it is. Structure of RDF graph will look something like this. If you're monitoring, let's say, environmental data, if you're monitoring IoT data, usually you will have different attributes. The important things are, let's say, if you're collecting measurement data, are the location information, which, for example, if I've shown has longitude, latitude, has unit of measurement, and then you can add, say, has value, has time, temporal information, and you can start creating more complex structure. We call this your schema. That's your basic, that's your template. And then once you have created that template, you start creating instances. And an instance could be, for example, a measurement 1, which has a value, has unit of measurement, and continues. Once you create an RDF document, this is a representation for just a modeling purpose, but RDF can be represented in different forms. One of the forms for representing RDF is in XML. But you don't have to represent it in XML, but one of the serialization, usually called RDF XML serialization. Angled right here is the RDF serialization. But you can use other forms to represent RDF. I'll show in a minute. Then once you create something like an XML representation, all the other flexibilities you have in XML, interoperability, being able to integrate it in XML or RDF sorts of databases, creating triple stores, being able to use this data, link it to other information already applies. Another advantage is now you can create structured information, and that hugely will help you to basically create pieces of information which can be linked to each other, and also allow you to structure your data better and analyze your data in a better format. For example, instead of repeating the location data every single time I show the location, I can create a location object here. And if I'm continuously monitoring temperature from this room, I don't need to send that location information all the time. I create a location and call it location, let's say 00AB1. And every time I'm collecting a temperature from this room, I just link it to that location. And as soon as you do that, you start creating linked data. You start creating structured information. Once you have done that, then you can start thinking of, I'll show examples of how you can actually index your data, how you can structure your data, and how you can use that information to integrate data from different sources. Then you can create millions of, let's say, instances of that measurement, and all of them can be linked back to a source, a location, which is an object location. Basically, are you familiar with object-oriented programming concepts? More or less like an object-oriented programming is object-oriented modeling of your data engineering. RDF has also some other interesting features. One of them is everything in RDF is represented as a URI. And you will know URIs are unique. Means already by creating that, you're also giving your data, your information, a unique ID. And that is very important when you are collecting data which is not associated to any address, because if you're like talking to a web server, I don't know, internet server, usually your identifier is IP. Anything you write gets translated to IP. But when you're working with data which can be transferred anywhere, everywhere, and you can collect data from different sources, you're having something like unique identifiers becomes an interesting aspect sometimes to be able to track that data. And sometimes also you can use some of those properties to add what we call a provenance of data to understand where the data came from. Do you find this useful? Or if you are thinking this is very slow, I can speed up this part and move to more practical aspects of it. Shall I speed up? No? Okay. In terms of the properties, once you're representing objects as URIs and you start modeling it, the properties becomes important. Like, in XML, everything was parent-child relationship, right? You create a tree structure, you don't actually tell much about that structure. Everything is just parent-child. If something is a subset of something else, without actually we know what defines that subset property. Here, once we have the graph models, once we have these properties, which link to things, this is called a property, right? This is, for example, is a subject, and this is an object, right? Subject, for example, my sensor, and this is the value, for example. These properties, they also can be defined. You can give them a name, you can give them a label, you can give them a unique URI. And then if you start creating something becomes a common name, a common vocabulary, then you can write interoperable programs. And in a minute, I'll show actually how you will move from this to the next stage, which will create a common vocabulary to be able to represent this information. But this is one of the more powerful ways of representing using RDF graphs. You're not just representing structures, you're also giving meaningful relationships to those structures. And then later on, you can write logical rules. If you're familiar with reasoning engines, you're writing logical programs, then you can write actually a series of rules to be able to extract insights which you didn't have before. For example, a very intuitive example, if you have a list of all the faculty members here in your website, if I go and search on Google, I can find a list of all the faculty members. If you have a web page, I can see everyone's name, I can click on and see their field of work. But if I want to find who are the best people in this department can collaborate with each other, I don't think search engines of today are very effective in answering that, because then you need to know, for example, I don't know, say I work on semantic web, Marco works on IoT, and probably IoT and semantic web, they have some relationship, and we can be potentially work together and create a project, right? But if you ask something like that from a web search engine, the most powerful web search engines, probably they will struggle. The reason is that because the information on the pages are designed for human eye. Basically, most of the search engines are the information locators. We search faculty members, University of Milano, and will give us a list of all the faculty members, but we'll leave the rest of processing that information. The difficult part is left still to us. Browsers render the information, but we do the most of the processing often. And these computers are becoming more and more powerful, but somehow still actually analysis of that data more or less is left to us. And if now in IoT or basically in semantics, we are interested in giving that part of that difficult task also to machines. Let's say if we represented everyone's interests, say in a structured graph format, and let's say, like now represented, let's say, I work on semantic web, for example, I don't know who works on IoT, and then on a higher structure, we say IoT and semantic web are related. Once you get that relationship, you can quickly relate us as well. That piece of information didn't exist. We call it implicit information, right? Explicitly, there is no indication. Potentially, we can work together, or our expertise can be linked to each other. But once you create a structured information and add a knowledge layer on top of it, suddenly your horizon for the machines to be able to read and understand that data completely changes. And that's what I was trying to say. When you add your machine intelligence with knowledge engineering, suddenly the power of machines to be able to read and understand that data completely changes. Then this is a combination of knowledge engineering and, say, logical processing or intelligent processing of the data. Since now we have created better structures. In XML, we could create the vocabularies, we create the structures, we added the tags. The problem was the tags in different languages, in different formats by different people could have different labels for the same concepts. And also XML was limited in terms of providing the relationship between data items. And what we did, we created a graph type of model. We use RDF, there are other ways of doing it. And we give more labels. We give labels, we create more structures, better structures, and we give labels to our data. But our basic problem is there, right? If still I can create an ontology, let's go back and look at this example. Here I've said has unit. Who says this couldn't be something else, right? I can still call it just unit. Somebody else calls it something else, right? In a different language, you can call it something else. And still we are, again, back to square one. Every time we solve a problem, we find there is another problem somewhere. It seems we have made some improvement. From the hierarchical structure, we have moved to graph structures. We can label our relations, but still we have this vocabulary problem. To solve that vocabulary problem, computer scientists, they have hijacked a concept from philosophy. In philosophy, there is a term called ontology. And ontology in philosophy defines the existence in universe. And I don't know, till very recently in Microsoft Word, if you type ontologies, Microsoft Word used to show a spelling error because it used to assume ontology doesn't have a plural verse, or always a singular, because there is only one ontology. But in computer science, you can have thousands of ontologies. And the idea is you start defining concepts and relationships in a domain. There are lots of complex descriptions of what an ontology means, but in principle, when we are creating an ontology in this context of the semantic technologies, we are trying to create a common vocabulary. From now on, if we can agree on an ontology, all of us, we call as unit, and nobody else will use different things. Basically, it's moving towards creating a common concept, a set of common concepts and common labels to represent those concepts and their relationships. Part of it is knowledge engineering, part of it is working with the domain experts. It means working with domain experts to be able to represent those concepts and agree on ontologies. Let's say in a concept of a university, if you're creating an ontology, you have university, students, faculty members, subject, schools, and you need to think of what concepts you have and how those concepts are related to each other. In terms of IoT, if you're putting sensors on health monitoring, you will say my sensors are monitoring the person, that person has a name, the sensor has an accuracy, has, manufacturer, has a time, has location it monitors, and so on. You start thinking of the concepts and the relationship, and you create your model. But there are also languages for representing ontologies. I'm not going to talk much about the languages. It's just a syntax. If you really want, one day you needed it, you can go and quickly learn and use it. There are tools to create this syntaxes. But the most common language for representing ontologies is called Web Ontology Language, or in abbreviation is OWL. It's probably easier to pronounce it. They changed the order and they made it OWL. OWL is based on description logic. If you're interested, is a logical language. It's designed based on the formal logic and description logic, and allows you to represent these concepts, their relationships, and add some constraints on that. Again, the syntax and representations you can look at are very similar, and there are some tools to allow you to create ontologies. I'm not going to talk much about the tools, but if you're interested, the most common tool is something from Stanford called Protege, and the website is called protege.stanford.edu. Probably if anyone can read my handwriting.
Natural language process.
Yeah, probably machines will struggle for years to read that. But basically, Protege, yeah, it's a famous tool and is used for creating ontologies. Then I started, I did my PhD on semantic web, and for the first few years when I got my first postdoc job, I started creating ontologies and semantic models for IoT. And after a few years, we wrote papers. Some of our papers got cited, and I've contributed to some of the semantic web modeling work. But one thing was interesting. After a few years, I noticed. One year I was invited to talk on the international workshop. There's an international semantic web conference, and every year there is also a workshop on semantic sensor networks. And that year I went and looked at some of the work we had done and my colleagues had done in this area in creating ontologies, and I noticed actually no one uses them. That wasn't a nice thing. I was thinking I would spend a few years of my time creating these models, and actually no one uses them. And apart from the research community or some of the work we have created, it doesn't really get adapted. That probably changed a lot the way we looked at our research and the way I started thinking about how we should do research. And again, that's why I'm trying not to talk about the tools and technologies, because these are the easy things. You don't need me. You can just go and pick it up and quickly start using the tool. But it's important to, whenever you do these things, to think of what problem we are solving and how that problem can help others in the community, or someone can actually be adapted and used in real world. And often creating an ontology is a simple thing. You need to just get people to agree on terminology. If they can if you can get them to agree on the terminology, then the representation is just a bunch of technologies, a bunch of modeling tools, which you can go and do that. But to get people to agree on the terminology, you need to go to your end user. You need to go to your customer. I cannot sit in my office and decide on creating an ontology for a healthcare application, and I'm going to use that, because the healthcare applications they have lots of legacy systems. They're creating already lots of data, or the people are going to get their devices, they have their own format and the language. And if I don't get them on board, or if you don't find a way to integrate that data, my ontology is not going to be picked up. Then in technical terms, in an ontology, see it as an object-oriented modeling. You will have a set of classes, you will have a set of properties which link these objects to each other. But in practice, It's just finding something which lots of people can agree, and you create terminologies which can be adapted by a large part of the community. When we were working on the W3C's semantic sensor ontology around 2010, there were lots of groups from different companies, from different academic groups, different stakeholders basically working together to agree what terminology we should use and what we should call, for example, I don't know, a sensor, what we should call a platform, how we should represent it, what are the properties. Part of that was lots of people had lots of existing systems. We needed to make sure we create a model which we can be somehow transform the data or be compatible with the existing systems. We wanted to make sure the model you create is also covers wide range of applications, parameters which the wide range of applications they need. And also we wanted to make sure that model is represented in a way which other people find it easy to use and to adapt it. Then there is no correct or wrong way, but there are some ways which can work better than the others. And there is no magic rule I can tell you, or you do this, it will work, depends on your application. In our healthcare scenario, I'll talk more about that on Friday, but our approach was when we were working with 10 different providers, part of the initial agreement was we will work towards a common language. Then everyone who had joined the project had already signed up to work towards a common language. The next step was we didn't go and created an ontology from scratch. We went and looked at what are the common terminologies are used in the healthcare domain. There's an international standard called HL7. I'll talk more about this on Friday, which is used to, or FHIR, which are used to represent healthcare data. For example, I don't know if in the UK I go and see my GP, my data is stored according to some structure, some format, which would say, doctor took my body temperature, and that body temperature will have a tag, will have some structure. They might not use the semantic technologies, but in terms of the vocabulary they are using, that vocabulary for representing that data is standardized. What we did, we went and looked at the existing models and we adapted that to our semantic model structure. Then if now we are using IoT devices to monitor people's blood pressure, in future we can potentially integrate that data with the existing healthcare data records. Now, if you're adding data in an industrial application, an industrial setting, probably you need to look at how people used to represent it. What are the most common ways within that sector for people to represent that data, and probably that will be your starting point. Then after you determine what is your domain, what the scope of that domain is, what concepts you want to represent at that domain, what application you're going to use, and then you start creating your classes, hierarchies, and a structure. I always say this part is the easier part. The technology, creating the models, representing it in semantics and things probably is just a set of tools, a set of steps, and we can be good at it. We can create good models. Creating something on the higher layer, which we can make sure other people will use it and will be adapted in the community we want and get the stakeholders on board, probably is less technical work, but is important. And then if you need to have a good ontology, you need to be good at both. You need to identify what are the common terms, what are the common requirements in that domain, and then you need to represent them very efficiently. I remember one of the early ontologies we have developed, being like I finished my studies and I was excited and I knew these technologies, and whenever I asked me to model, I tried to add as many features as I can, right? Create complex models. And once we had created this ontology for representing IoT data, and we had, 50 different parameters to represent that data, and we were using some complex format to represent that. And one day, my colleagues in our group were deploying some smart campus IoT infrastructure. And they came up with this idea. They said, okay, if you're developing sensors and you work on the semantic technologies, if we can add the semantic interoperability models, we can also open up our data. We can create an open data, open campus, which people can use all around the world. We can share the data. It could be an interesting infrastructure. They came to me and asked, can we use your model to represent our data? And I asked, how many sensors have you got? He said, around 200 sensors. And I opened and I looked at one of my data structures, and I looked at for every sensor, I need to represent 50 different parameters. When I started thinking of each of them, I've created a couple of examples. I've written my papers based on some examples, but I've never thought of actually creating tools to be able to create that data structure. I never thought of actually the complexity I'm adding. These are important things when you create an ontology. When you create an ontology, you need to think of the users. You need to think of the scalability of that model. Complexity is not often good. As people probably like, sometimes we like complexity because it looks good, we can write good papers on it. But in practice, you need to think of what are the key requirements, or at least create structured models. I changed my slides because I'm trying to speed up a little. I showed RDF structures, but over the years, RDF is still, people will have different opinions in this. My opinion is RDF hasn't been as widely adapted as some other formats on the web. If you look at most of the common web platforms, most of the new applications basically are developed, most of the common new programming frameworks, they adapt JSON. And JSON becomes more and more widely accepted and widely used. And most of the web applications somehow rely on some sort of JSON data exchange. Have you used JSON in any of the programming? You're familiar with JSON infrastructure. It's just an object property model. Right? I've provided an example of that. It's just a comparison between XML and JSON. It's just a format. Over the years, JSON seems to be becoming more like a de facto standard for developers to represent their data and exchange data over the different web platforms. And obviously, if you want our semantic data to be adapted, one way of also thinking of it is not just creating our models which become adaptable, also looking at how we represent our data, because you have different stages. You look at the requirements, you design your system based on the requirements of people, you start defining the right and adequate level of complexity in your model or creating more modular models. At the same time, when you represent your data, you need to think of what type of formats are the most efficient way can be adapted by the community. Then over the years, people were working on the semantic web, they have realized if you can embed or include semantics into JSON, probably you increase the chance of actually the semantic technologies being adapted. The earlier versions of this probably would have been HTML, which was the idea of embedding semantics into HTML. I don't know whether that standard still exists, but if you search on W3C, probably, I don't know, I haven't seen it for a while. Probably not. Then there is a concept called JSON LD, which is basically JSON with semantics embedded. And I'll show an example of a JSON LD in a minute, but before doing that, I noticed actually I didn't define what a linked data is. Do you know what linked data is? The notion of linked data is, again, Tim Berners-Lee a few years ago wrote something which was published on W3C's website. I don't know whether he was the first person, or I've seen, the first time I saw linked data, I saw Tim Berners-Lee's definition. Let's say he was the first person to use that. And the idea of a linked data is everything you represent has a URI. Then any object you represent has a URI. And if you refer to that URI, you will get a semantic or a meaningful description of that notion, which we were saying, like if you're representing a sensor measurement, that sensor measurement has a URI. And if I refer to that URI, I'll get some description of different attributes of that data, context of that data. And that's the second rule for creating linked data. The third is that data should be also linked to other information. For example, if I'm monitoring information from this room and I say this room has a URI first, that data itself, I can refer it with a URI, find that data, could be a RESTful service, which gives me that data. If I refer to that, I should be able to get some semantic description of that data, saying these are the parameters of accuracy, location, time. And also, ideally, you want that data to be linked to something else. For example, to say this data comes from the computer science department at University of Milan. And if the University of Milan has a semantic description, you just link it there. And that's the notion of linked data. Now, JSON LD is basically creating linked data or semantic descriptions using JSON. I guess if you look at the description, you will find it easier than what I explained. Basically, there are semantics embedded into JSON data. If you look at some of those properties, now they have a URI, and those URIs can give you the semantic descriptions or could have semantic meanings, or you can define unique properties, unique vocabularies for defining each of those. Because instead of now adding labels, I'm adding unique URIs, which could come from an ontology, could come from a vocabulary. Yes, please.
Is this like a parallel concept as an XSD in XML?
Yes and no. Yes, because yes, it is, and no, because XSD will give you only the data types and has more or less a constrained, contained set of definitions. Here, you can create your own ontology. Let's say create your own ontology for the measurement of data and embed those concepts into your JSON. Let's say in JSON, instead of allowing people to create their own labels, they can add labels from your vocabulary, from your ontology. But in terms of the conceptually how it works, yes, exactly, it's very similar to XSD.
Because the ontology itself is defined with some JSON format?
The ontology itself can be created actually can be represented in OWL and RDF.
Okay.
But the URLs to say what that ontology is embedded into JSON.
I see.
You're right. It's just in terms of the scope, is more open than XSD. And also in terms of representation. Then there are different concepts. Sometimes also, because these URIs are really long, and if you start repeating them, you're also creating lots of overhead, and you're making your syntax complex. There are two things. If you can make those syntaxes shorter, first of all, remember my example of I showed the devices, but then they send lots of information. They are basically using battery power. If they're sending this information over the air using battery, you want to make the syntax more compact as possible. And sometimes you want to make that context also, that syntax easier to read and interpret. Then JSON-LD has something, if you're familiar with XML namespaces, you can create something like a namespace. Then you make this, basically instead of adding just URIs, you always add basically the namespace, and you say, basically make your URIs shorter. And that's called context. And you define where your context is. Sorry, the color contrast is not very easy to read. Right. So far, let me discuss now. We started from very syntactic data, syntax-based, comma-separated data. And we discussed the limitations. We said interoperability and integration is challenging. We discussed the XML. And then we said in XML, the labels could be different. The structure didn't say much about the relationship between different properties. We discussed creating RDF, creating more graph structures, and we faced the problem of the vocabulary. We discussed the concept of designing ontologies and creating common vocabularies which can be accepted. And we looked at different ways of representing data. Once we have done that, we are creating a potential for making this IoT data more interoperable. Basically, you can get the data from different sources. You can include data from the multiple providers. You can start looking for your resources. Indexing and finding your resources becomes easier. And also, you can write rules now on top of that data. Because if you know always someone's body temperature will come with a certain vocabulary with certain properties, you can write rules which can work universally across different applications, across different platforms. You will say always when you see someone's body temperature, this should be in the range of, 36 to 37.8 or 9. And if it goes below or higher than that, generate an alert. And always you know how you can separate different properties from your data because you know the ontology, you know the structure of that data if that data is represented in a structured way. Now, in some practical steps, if you're designing that model and if you have created that model, what are the practical steps to make sure that model being widely adapted, and what are the ways of actually be using that data and making that data more usable? One of the first things is creating lightweight ontologies, because especially in IoT, constraints with resources and the scale is different. And if you're creating something very complex, in my example of having 50 properties, for example, to represent a data, you need to think of whether you need all those 50 properties. It's better to create more modular structure instead of like asking people to provide lots of attributes, maybe create different components and people can plug in different components based on their need. Very similar to object-oriented programming, like different basically inheritance model or different classes. Compatibility is very important. You need to create models which can be used across a wide range of systems. The compatibility of how you represent your data, the choice of whether you choose to use RDF serialized in XML. I didn't mention RDF can be serialized in other forms as well. There's a format called Turtle. You can just look it up. There are different forms. Deciding on how you're representing that and the compatibility with different systems or different stakeholders you have is an important thing. And also compatibility of your vocabulary, the terminology you use. The more you can use and adapt existing terminologies, make the work gives a higher chance to be adapted. And obviously you need to think of to create something representative enough, but the model should be lightweight to increase the chance of it. One of the very good examples of creating models, which started around 2010, is SSN ontologies. It stands for Semantic Sensor Network Ontology. This is a work started as an incubator group at the W3C. Do you know what W3C is? It's World Wide Web Consortium. It's the body that standardizes the web. All the HTML, all the web standards sort of comes as the W3C recommendations. And W3C Semantic Sensor Network Incubator Group started looking at, if you want to model a sensor as a device, what properties we need, what components we need. And this was a collaborative work, international, looking across different sectors, different stakeholders to create a model. The very first version looks something like this, which is a bit complex, but as soon as the group were working on it, they created this model, they realized, first of all, you need to create structure. You need to create structure where people look at that part which they need and they can represent only that part. Maybe I'm only interested in representing like the accuracy parameters of my sensor and the operating part of it. Maybe the other components are not relevant to me. And I can plug and play different components like that. Basically showing different concepts. Let's just pick one. A sensor is a sensing device. A sensing device is a device, and a device is a system, and creates basically a hierarchy of concepts and the relationships. This is the early generation. In a few slides for
between the sensor and the sensing device.
Sensor is a sensing device. I think is a subset of a sensing device, if I'm not mistaken. And a sensing device is a subcategory of a device, and so on. I think these are like hierarchical structures. This is a subset. Yes. The early generation of SSN focused only on the sensor as a device. Didn't focus on observational data. And the next generations of SSN, you will see, and the works followed up after that, started adding observation data. You can see the structure, as soon as you start modeling it, can look very complex. And easily you can add more complexities. Easily you can add more and more, basically labels to it, more structure into it. One of the things will be very important, if you're creating something like this, or if you're creating any semantic model, one of the important things is to think of creating tools. It's not just creating models, creating tools which can read that data, can allow other people to format data according to your model, and also showing some examples of best practices, how that data can be used. Again, in our healthcare application, when we started creating our ontological model, one of the very first things we did, we wrote some Python libraries. And we told people if they give their comma-separated data, they can feed that to our Python model, and our Python model can create semantic descriptions out of that. We wrote applications on top of that which could get different parameters and feed it to different machine learning algorithms to use that data. And once you create the chain to that data to be used, then you're increasing the chance of your data being adapted, your model being adapted. Just creating a simple model and showing a couple of examples is not often enough. Would you like to have a break and continue? I have another 50 slides. Or shall I continue? Okay, I need to pause this. Let me find how can I do that. No. So I'm just trying to figure out just how does the screen works.